Hi there, today we have a very interesting question and it's based on linear transformation coming from the linear algebra course. We have this question given that t is such that R3 is mapped onto R3 by t into x, y, z, where that's going to be equal to 2x plus y, y minus z, and 2y plus 4z. So we need to verify that t is a linear transformation. So what we are going to do now, we're just going to try now the solution to this problem. Okay, so I'm going to let alpha be a vector in R, which is x1, y1, and z1, and also beta is equal to x2, y2, and z2. Right, so the first thing I'm going to do is I'm going to try the transformation on alpha plus beta. So if I have alpha plus beta, I'm going to get x1 plus x2, then y1 plus y2, then also I have z1 plus z2. And now if I were to apply my transformation on alpha plus beta, which are the two vectors in that vector space, in that field, so what is a transformation? A transformation is when we apply on x, we get 2x plus y, 2 of x plus y, so over here 2 of x, 1 plus x2 plus the y. Okay, and the y is now y1 plus y2. Okay, and then the second one is going to be y minus z. So my y is this and z is that. So then I'll get y minus z, and y is y2, y1 plus y2 minus z1 plus z2. And finally, I've got z being transformed into 2y plus 4z. So 2 lots of y, so that means 2 into y1 plus y2, okay, plus 4 lots of z, and z is z1 plus z2. Now that's my transformation after we've applied it onto the two vectors. This now what I'm going to do is I'm going to try the transformation on the vectors separately, distinctly. So if I apply my transformation on alpha, and because of alpha, we let alpha equal to x1, x1, y1, z1. So we're going to get this transformation 2x plus y. So this is 2x1 plus y1. So that should have been 2x, hang on a second, 2x1 plus x2, okay, plus 1. That's okay, that's fine. Then my second transformed element is y minus z. And over here, I've got y1 minus z1. So I've got y1 minus z1. Then I've got 2y plus 4z for z. So for z, I've got 2y, so that means 2 y is y1 plus 4z and 4z1. So that's my coordinates after it's been transformed. And what about the t beta? So if I apply my transformation on beta, on the vector beta, I'm going to get then 2x2 plus y2. It's the same thing. So y2 minus z2, and I'm going to get 2y2 plus 4z2. So 2y2 plus 4z2. So we're still doing quite good there, and these are my transformed vectors. We're going to try now to add these two vectors. So we're going to say t of alpha plus t of beta, okay, added. So I'm going to take my alpha, which is 2x1 plus y1, add to this one. So I've got then here 2 lots of x1, 2 lots of x2. So 2 lots of x1 plus 2 lots of x2 plus y1, okay, plus y2. So I got my y1 plus y2 plus y1 plus y2. And now I also have for this coordinate now, the y coordinate is y minus z, y1 minus z1 plus y2 minus z2. So y1, okay, that's going to be y1, is that y minus z? Yes, so y minus z. So y1 minus z1, okay, minus y2 minus z2. Okay, so minus y2 minus z2. Now, if I want to simplify this, it's a y1 minus y2 and z1 minus z2. So I have y1, okay, y1 minus y2, okay, y1, this is my, okay, y1 minus y minus z, so y minus z. All right, so here we go, y minus z. Is all right? So if I were to add these up, so I'm going to add these two. So y1 plus y2, sorry about that, y1 plus y2, and then plus minus, I would say, z1 plus z2. So z1 plus z2. Right, that's great. Then I'm going to add these two up, the third element, so 2y1 plus 2y2. So I've got then 2 into y1 plus y2, okay, plus then I've got the 4z1 plus 4z2, so plus 4 into z1 plus z2. Now, as can be seen, okay, this t of alpha plus t of beta is equal to actually t of alpha plus beta. So what we can see, we're going to observe that therefore t of alpha plus beta is equal to t of alpha plus t of beta. So basically now what we're saying is that the additivity property is satisfied, or it holds, is satisfied. Right, so the second one, the second basic one I'm going to take now is I'm going to say, let me apply C of t, the C of t alpha, C of t alpha. All right, so what I'm going to do is I'm going to try t alpha first and then multiply by C. All right, so, or maybe I'm going to apply my transformation first on C alpha. But what is C alpha basically? So first of all, I'm going to compute C alpha, which is then, we are going to try to let C be any arbitrary constant. So I'm going to write this down, okay? So let C be any arbitrary constant, okay, in our field R. Now, if that's the case, then I'm going to say T C of alpha. So, but first of all, I want C of alpha. And what is C of alpha? C of alpha is my vectors. My vector alpha, rather, I would say x1, y1, z1. So x1, y1, z1. So if I were to apply this, I'm going to get cx1, cy1, and then cz1. So what I'm trying to do now is I'm going to try to apply my transformation on C alpha. So apply transformation on C alpha. And I'm sure you're going to refer back to the transformation here. So 2x plus y would be x. So cx1 is going to become 2cx1 plus y, and my y is cy1. So that's my x transformed. And my cy1, which is the y here, becomes y minus z. So y minus z. So y is my cy1, okay, minus cz1. And then I also have z transform into 2y plus 4z. So z transform into 2y plus 4z. So cz1 transform into 2y. So this becomes then 2cy1 plus 4z. And z is cz1. Okay, so plus 4cz1. Now that's my transformation. And if I were to just put the c outside, I'm going to get 2x1, y1, so c, and then 2x1 plus y1, and then I'm going to get here y1 minus z1, and over here I'm going to get 2y1 minus 4, I would say, or the plus, because of the plus here, 4z1. Now this is my transformation on C alpha. Let us see if this is going to correspond to, what if I say now, I put my C outside and then apply the transformation on alpha. And if I were to apply the transformation of alpha on alpha, first of all, I'm going to try my T alpha. So what is T alpha basically? Transform the vector alpha, okay, into the image here. Now, alpha is basically x1, y1, z1. So if I were to transform this, I'm going to get 2x1 minus, or rather plus y1. So 2x1 plus y1, y1 minus z1. So y1 minus z1. And I got 2y1 plus 4z1. So put 2y1 plus 4z1. Sorry. Now that's my application of the transformation on my vector alpha. And now I'm going to multiply this by c. So to see ct of alpha, okay, is going to be equal to the c multiplied by all of that. So that's going to become c into then 2x lots of 1, 2x1 plus y1, then y1 minus z1, and I also have 2y1 plus 4z1. As can be seen, this whole thing here is exactly the same as this here. So can you see here C and C, and every element inside is the same as this. All right, so what are we essentially saying? That TC of alpha is the same as CT of alpha. So we can see that the scalar multiplication is satisfied. The scalar multiplication is multiplication property, whatever you may call it, is satisfied. Now since, okay, T of alpha plus beta is equal to T of alpha and plus T of beta, and also T of our constant times alpha is equal to then the constant times T of alpha. Therefore, T is a linear transformation. And hence, okay, and hence T is a linear map on VR. A transformation is VR3. Okay, so here we are. I hope you've been able to make sense out of this. Just a small question on linear transformation coming from the linear algebra module here. Linear algebra. I hope you've enjoyed this video, and I really appreciate and thank you for your attention. Take care.